Community-based supply chains operate in highly volatile environments where raw material inputs are entirely at the mercy of the weather. In small-scale coastal fisheries, a sudden shift in ecological conditions or a break in a storm can trigger a volatile, completely unpredictable spike in fresh fish landings. This chart plots those erratic daily supply spikes against market demand for processed fish, which follows a smooth, highly predictable seasonal consumption curve. Those severe structural gaps, where the raw material intake vastly overshoots the baseline processing capacity, represent a critical failure point. Because the surplus raw fish cannot be processed and safely stored in time, producers are forced into low-margin distress sales to move the inventory before it spoils. Addressing this structural mismatch requires a first-principles approach. By integrating time series forecasting, the theory of constraints, and linear programming, chaotic intake can be mathematically mapped to feasible operational capacity. This pattern suggests that chronic underutilization in these supply chains is often a symptom of unmanaged systemic mismatches in timing rather than a lack of physical resources. Before any mathematical optimization can be applied, operators must map the physical constraints of the processing plant itself. This process flow diagram tracks the plant's operations, from preparation into sun-drying and finally cold storage. At preparation, human labor caps daily intake around 300 kilograms. Compare that to sun-drying, where process time stretches to 14 days per batch. The theory of constraints dictates that any production system is ultimately governed by its weakest link. That single point dictates maximum throughput. Here, sun-drying is clearly identified as the system's dominant bottleneck due to total weather dependency and extended cycle time. Without mathematically managing this specific constraint, sudden raw material spikes will generate growing work-in-process queues and immediate financial loss. To prevent raw materials from crashing into that drying bottleneck, operators need a method for predicting their daily input volume. The analytical challenge is that historical catch data is intensely volatile. A static production plan cannot be built on random noise. Researchers tested 3 distinct forecasting methods: simple moving average, weighted moving average, and exponential smoothing. While moving averages struggle to map variance, the exponential smoothing line effectively filters noise to extract a usable signal. The proof is the mean absolute percentage error. Exponential smoothing maintained a 144% error rate, far outperforming the simple moving average's 409%. In stochastic systems, a forecast is not a crystal ball. It acts as an operational baseline to align management expectations with feasible actions. With the physical constraints identified and the input baseline set, the chaotic reality of the processing plant can be translated into an auditable linear programming model. The objective function is defined by a single goal: to minimize opportunity loss. The system must process as much fish as possible to avoid selling raw inventory at a discount. The model relies on decision variables representing discrete actions on the factory floor: processing the fish, selling it raw, or holding it in storage. These variables are bound by strict rules, starting with the supply balance constraint. The system cannot process or sell more volume than the daily catch. Next is the critical bottleneck constraint. The physical limitation of the sun-drying racks creates a hard mathematical boundary. Finally, the inventory balance constraint mathematically links the individual time periods together by tracking the carryover cold storage from one day to the next. This strict mathematical architecture forces the system to calculate daily operational decisions that maximize total value, entirely governed by the physical reality of the plant. When this baseline model is run through a solver against peak seasonal supply data, the limitations of the current operation become completely transparent. While immediate financial losses decrease slightly, the math proves that the existing sun-drying bottleneck continues to force persistent production backlogs. Optimization alone cannot bypass physical reality. The solution requires executing another theory of constraints principle: elevating the bottleneck. You add physical capacity only at the exact point where the math shows the system failing. Simulating the addition of 2-tier drying houses demonstrates how to directly address this constraint, boosting throughput by 500 kilograms per day. This is paired with a complementary intervention, expanding the cold storage freezers from 200 to 600 kilograms to act as a primary shock buffer. Running the model with these newly elevated constraints produces a different outcome. The solver immediately reroutes the variables to push maximum throughput, and the work and process queues instantly clear out. Targeted physical investments, when precisely directed by an optimization model, yield measurable systemic efficiency without the need for broad capital expansion across the entire facility. To measure the final impact, researchers ran a 5-year economic valuation simulating the financial outcomes of this optimized system. This dashboard shows the result: a benefit-cost ratio of 1.95 and an internal rate of return of 32.49%. These high returns validate the engineering framework, proving that precise bottleneck management is highly viable from an economic standpoint. The broader lesson here is that deploying advanced operational analytics does not require custom software or supercomputers. These structural optimizations were completely modeled and executed within a standard spreadsheet environment. The data confirms that economic instability in these operations is driven by unmanaged volatility, weak coordination, and misaligned timing. By isolating the dominant physical constraints and enforcing strict mathematical logic, stochastic supply chain chaos can be engineered into a resilient and highly profitable system.